In progress.
How you doing, Jordan and Nicole?
Good, how are you?
Oh, peachy keen, wonderful. Neither one of you have started this lab yet, have you?
No.
I tried to, but I decided to stop and like wait for you to explain it.
The main problem, Jordan, I literally I was going like this on Saturday. The main problem is the problem they give you has nothing to do with what you're doing today. Okay, you know there was a problem in the simulation, Jordan.
Mm-hmm.
You don't have to do that problem. As a matter of fact, I would encourage you not to do the problem, because when I did it, it worked for the ammonia buffer. It didn't for the acetate buffer. There's something about the program, I think, that's a little wonky that doesn't give the right answer. So it's either that or I've got something fundamentally wrong with the way I'm solving the equation. So don't do, if you want to do it for fun, do it for fun. But it's not, I'm not going to look at it and it's not going to be graded, okay?
Okay.
Raylena, you haven't started the program yet, have you?
No.
Okay. Guys, in a way, this is a really fun lab because there's, all you're doing is you're doing science. That's really and truly all you're doing is you're doing science. You're doing things that he asked you to do and making observations. Okay? So in other words, you can't get anything wrong. All right? Put an answer in the block and you'll get credit for it, okay? There might be one exception to this, but the actual data you're putting in there, I'm not going to mark anything wrong on it. We good with that? All right, fantastic. Okay, I'm going to get into sharing the screen and we're going to get to the simulation. Part A, all you're doing is following his directions as best you can in the simulation. Okay. Can you see my screen, guys?
Yes.
Jessica, you're seeing it, Jessica? Good. Okay. Hopefully I won't lose you when I go through the different things here. All right. Okay, when you pull this up, it gives you a little bit of an introduction. Has everybody had Henderson-Hasselbalch or buffers at this point? Nicole, are you in my lecture?
I'm not, but we covered this in my class.
No, that's fine. Raylena, yeah, you're in the lecture, right, Raylena?
Yes.
Okay, that's good. So you at least have been exposed to what the Henderson-Hasselbalch is, and it's really a quite useful equation because it gives you a way to make buffers at pHs other than where the pKa is. And it's fairly simple to use as long as you know how to use logs. It's a fairly easy method to do it. We're going to modify it today in the second part, but for right now, what you're seeing right here in equation 3 is the Henderson-Hasselbalch equation. And it shows you how to get the pKa. And simply what you're doing is you're taking the ratio of the concentration of A- over HA. Now let's think about what that's really doing. A concentration is moles per liter, right? Somebody shake their head. Concentration is moles per liter, right? So we have moles per liter over moles per liter, right? In order to make a buffer, don't the conjugate acid and conjugate base have to be in the same solution? Don't they have to have the same molarity? Shake your head, Jessica. They have to be in the same liquid, right? So if they're in the same liquid, they have the same volume. Look what that does to this part of the equation. I got moles per liter divided by moles per liter, but the liters are the same. So in actuality, what I am really doing is comparing moles of A minus to moles of HA. Does that make sense to you guys? Thank you for cooperating, Jessica. Are you yawning? Okay, so basically that's the Henderson-Hasselbalch. Now, if you want to, it gives you a couple sample calculations to do the problems. All right. Now, it would be a good idea to watch his introductory video or watch the introductory video to, it's the same, it's one of the same simulations you've used before. When you see it, it's going to be very familiar to you. Jordan, did you have any problem assimilating this chem simulation to the last one?
No.
Okay. There is a report sheet. Are you seeing it pop up now?
Yes.
So literally speaking, guys, for part A, all you're doing are the instructions that are given to you, and all you're doing is putting in pHs here. Okay? Now, part B is a little bit different. You're going to have to go to the survey, and that will tell you what your weak acid is, and it will tell you what the buffer is. It may or may not tell you what the pKa is. I don't remember at this point. But I'm sorry, it may not pKa. It may or may not tell you what the Ka is. But that's easy enough to change Ka to pK. If you're not given it, you should be able to Google the Ka of the weak acid. If that doesn't work, try the appendix in the back of your book. The appendix in the back of your book has the buffers. Okay? Now, what you're going to be asked to do here is you're going to be told, I want a pH of a buffer. Okay? And you're going to be told the acid, which means you're going to have the Ka. The instructions tell you how much of the weak acid you're going to start, the volume of the weak acid. What you're going to do is you're going to use the Henderson-Hasselbalch. I'm going to modify that equation slightly. And you're going to use that modified equation to determine how many milliliters of strong base you need to add to make your buffer of that pH. Then you're going to use the simulation to determine how far off you are. Does that make sense about part B? Does that make sense, guys? So let's get into the simulation. Okay, I'm getting out of here. Oh, one more thing while I'm in there. I just want to make sure. Everybody's still seeing the report sheet, right? All right. It asks you some questions, some basic questions about the adding, and these belong. The first question, part A. Second question, part B. Then you're being asked in part A to make a buffer of 2 milliliters weak acid, 20 milliliters of base. Then you're asked questions about adding NaOH to the buffer and adding you're just being asked the NaOH. Next question, you're going to add HCl to deionized water. Ask, does it change? If you put acid in water, what do you think the pH is going to do? acid and water, guys. Thank you very much, Jessica. The pH is going to go down. If you add NaOH to water, what do you think the pH is going to do? Come on, Jessica, help me out here. To base, I'm adding base to water. Thank you. If you add base to water, it's going to go up. And the only thing this is trying to do is it's trying to make you think. It's trying to show you that when you add a buffer, when you add a base to a buffer, the pH doesn't change that much. But when you add it straight to distilled water, it does change. Okay, part B, you're going to be given, again, in part B, you're going to be given a target pH. And you're going to be given the weak acid, so you're going to know what the pKa is. Now, you're going to have to go through the calculation to determine how much NaOH you need to make that buffer. Then you're going to actually come and determine how much you actually did and does it agree. Okay. pH of a okay. You know, at this point, you have an acid, okay? You have the Ka. At this point, you're just doing an ice problem, okay? You have you're going to be able to figure out what the Ka is because you're going to look it up. I'm sorry. I'll give you instructions on how to do this one. Just got to think about it. Okay, if this is a straight Henderson-Hasselbalch, I'm going to show you how to do the equation. And I'm going to show you how to do the equation, and you're going to be able to do it from there. And again, I'm going to show you how to do this in a few seconds, okay? Let's get to the simulation. Everybody's saying the buffer solution with a specific pH. I'm not saying it. Thank you. Okay. What I would do with this is I would go back and have, first of all, are you seeing my screen? All right. I would go back and make two icons at the top here. One with the instructions, one with the simulation, so you can toggle back and forth. Okay. First thing, take 15 milliliters of 0.1 acetic acid, put it into a clean beaker. Then you're going to take sodium acetate, put it into a clean beaker. Then you're going to mix them together and do the pH. Okay, you have solutions. These are the solutions. We need acetic acid. Go back to the stock room. We need sodium acetate. Go to the stock room. We need, we're going to do a graduated cylinder. Graduated cylinder. We need a beaker. Okay. Are we good, guys? We understand? So basically, we're going to need to have our acetic acid. Look at the left right now. If you look at the left right now, at the very bottom here, you're going to see the pH. This is the pH of whatever you have grabbed onto. Okay. Now we'll see how that's going to change in a second. Again, you got to put one over the other. Now, in one point, you're going to be asked to add 5 drops of NaOH. For that, you're going to need to go significant figures and put, like, I think he tells you 0.25 milliliters. So you enter 0.25, then pour. Okay. But if you're just doing a regular buffer, you're going to add 15. You're going to be in the precise mode. Pour. I got 15 milliliters in my graduated cylinder. Okay. Put that back. Grab my beaker. Put this in here. Okay. Now I've got my 2 solutions in there. Did I have? Okay, no, I got to add 15 of this. Now, if you noticed, look what happened to my pH. For the acid, it was 2.88. When I mixed the 2 buffers together, it's 4.76. I think you're going to have to record that number. Okay. Now, calculate the pKa of the acetic acid. A real nice thing about the Henderson-Hasselbalch, which is equation 3 up here. If the concentration of the conjugate base equals the concentration of the weak acid, this is 1/1 then, correct? Jordan, shake your head. If it's 1/1, then I have the log of 1. The log of 1 is simply equal to 0. So I have added equal amounts of my acid and base in here. And I've got a pH of 4.76. Can anybody tell me what the pKa is? You done yawning, Nicole?
Yeah.
What's the pKa?
4.76.
4.76, guys. All right. Just for kicks and giggles. I don't want to, you're going to have to go through the entire simulation. That's as far as I'm going to go with this. All right. But I'm just for kicks and giggles. I want to see if you can save some time. Ooh, looky there. You don't have to go through the silly graduated cylinder. Looky there. So guys, if you don't want to bother going through the graduated cylinder and then to the beaker, just take it straight out of the flask, all right? Are we good kind of with what you're being asked to do here? You're asked to first make the buffer. Then what you're going to do is you're going to put 30 milliliters of DI water on top of the 15 plus 15. So you basically have a diluted sample. Jordan, what do you think the pKa of the diluted sample is going to be?
Like the 1-to-1 ratio.
If it was 4.76 for the concentrated, it's also going to be 4.76 for the dilute. Okay. So they want you to do that just to prove that diluting the buffer doesn't affect the pKa. All right, you're going to separate. You have 60 milliliters. You're going to separate that into 2 beakers. To the first beaker, you're going to add 5 drops. Again, 0.25 milliliters. You're going to have to go to the precise, the sig fig measurement to get it exactly. So you're going to take 0.25 milliliters of 0.1 molar NaOH. You're going to add that to the first beaker, measure the pH. Don't use that one again. To the second beaker, you're going to add 0.25 milliliters of HCl. Measure the new pH. Basically, what they're trying to do here is they're trying to prove that if you add a small amount of acid or base, you're not going to change the pH significantly. All right? At the end of that, you're done with that one. You're going to make a third buffer. To this, though, you're going to measure out 2 milliliters of the acetic acid, and you're going to put 20 milliliters of sodium acetate in the beaker. You're going to mix them in, and you're going to determine this pH. You're going to calculate the pK again. Now, when you do the Henderson-Hasselbalch, the pH is going to change. pKa doesn't change. The pH changes because you have messed the concentration of the conjugate base and acid up. So the pH is going to change because of that change in concentrations. So you're going to use those numbers, plug them into the Henderson-Hasselbalch, and solve for pKa, compare it to what you got when you mixed them. Then you're going to throw 3 milliliters into the 2x20 buffer, measure the pH. You're going to do that into 1 beaker. Then you're going to add 0.25 milliliters of HCl. Put that into that buffer. See if there's any drastic pH change. Measure 25 milliliters of water. Put it into a beaker. And you are going to, erase that. You're going to take 0.3 milliliters of the 0.10 NaOH, add it to the buffer, observe the pH. Then you're going to take distilled water. You're going to add acid to the distilled water, and you're going to add base to the distilled, 2 separate distilled water solutions. And basically what this is doing is this is going to say, okay, I've challenged the buffer. So the pH is going to change a little bit, but it's not going to nearly change as much as this small amount of acid to distilled water or the small amount of base to this distilled water. Is this kind of making sense, guys?
I have a question.
I'm here, Jennifer.
So on the sheet, it says 20 milliliters of the conjugate base buffer system after adding HCl to the 2 millimeters of the weak acid.
Okay,
On the
which step are you on?
1, 2, 3. Let me see.
Aren't
so
they
you know
numbered?
where it says number
Jennifer,
17?
aren't they numbered?
Number 17.
Okay. All right, you're making the 2 to 20 buffer. In other words, 2 milliliters of acetic acid is going to be put in a beaker. Then you're going to add 20 milliliters of the conjugate base, the sodium acetate, to the beaker. You're going to measure the pH. You're going to calculate the pKa again. Okay, Jennifer?
Okay.
Then to that beaker with the 2 to 20 ratio mixture, you're going to add 3 milliliters of 0.1 base. And you're going to measure the pH.
How much HCl do you add though?
None.
None?
At 17, all you're doing is you're adding 3 milliliters of the NaOH to the 2 to 20 buffer. Okay?
Okay.
And you're adding and you're seeing if there's any pH change.
So on the sheet, do we just put like 0 after adding HCl? Because that's one of the questions that it asks.
Crap. You gotta love it. Thank you, Jennifer.
Welcome.
I see. He missed a step. There should be a step 18 in there. Okay, he missed a step in here. And basically you add 3 milliliters of 0.10 HCl to see if that changes the pH. Because it's, Jennifer,
Yes.
because it's not in the procedures, I'm not going to take off if you don't fill that in. All right.
Okay.
That's the easiest way I can solve this. I'm sorry, I didn't see it when I was going through there. If you want to do it, it's not going to hurt anything. Fair
Okay,
enough,
thank you.
Jennifer?
Yeah.
Okay, you're right. You're right. Thank you very much for pointing that out to me.
You're welcome.
All right. After you've done that, then throw that one away. You don't need that one anymore. The next thing you're going to do is you're going to add a beaker of water and you're going to add the HCl to that. You're going to have a second beaker of water. You're going to add the NaOH to that. Fair enough? Just give me a second. See where this is at. Drops it out, measure the new pH. Yep. Okay, I understand why you missed it. Okay, thank you, Jennifer. It's not in the original, it's not in the original procedures, but it's in the data table for the original one as well. So thank you, Jennifer. All right, let's deal with the second half. And to this, I'm going to stop share for a second. And I am going to go to the oh, there it is. I'm sorry, I couldn't find it. All right, ladies and gentlemen. All right, basically, this is the Henderson-Hasselbalch equation, where you get the pH is equal to the pKa of the acid you're working with, plus the log of the conjugate base over the conjugate acid. Now, the best buffers occur when the conjugate base concentration is equal to the conjugate acid. In other words, when the pH is near pKa, that is the best buffer. Okay? Now, the normal way to make a buffer is what you did in the first instance. You measured out 2 milliliters of your acid and 20 milliliters of your conjugate base and mix them together. Does this make sense, guys? Now, there's another way to make a buffer. What happens, guys, when you add a strong base to a weak acid? What do you make? If I add KOH to acetic acid, what am I making? I'm adding an acid and a base together. What are my products? Come on, I know it's 8:30, but
Is it salt and water?
salt and water. So the KOH, the potassium from the KOH, is going to hook up with the acetate from the acetic acid. So I get potassium acetate. Isn't that the conjugate base for acetic acid? So literally what's happening when I add my strong base to my weak acid, because I'm making potassium acetate, I'm creating my conjugate base. Now, if I have some weak acid left over, don't I have a buffer? Because I've made some conjugate base by adding the strong acid to my strong base to my weak acid. So I've made some conjugate base. If I happen to have some weak acid left over, I've got a buffer. I've got my weak acid and my conjugate base and my weak acid. So the way to do this is you add less strong base than you have weak acid. So you make sure that you have some weak acid left over. This is just another way to make a buffer. Now, when I'm doing this, as long as the concentration of my strong base is the same thing as my concentration of weak acid, that has to be true. Then you have to write this equation down, guys, because it's not in the stuff that he gave you. As long as that happens, then the pH of your buffer is going to be equal to the pKa plus the log. You're going to take your This is why I need to edit before I do something. You're going to take the milliliters of strong base that you're putting in your buffer, and you're going to put that over your milliliters of weak acid you added it to, minus the milliliters of strong base. So let's do a problem, and we're not going to use acetic acid. I'm not going to use acetic acid because that's what you're using in the, you're going to use, I'm going to say formic acid.
Professor, what were you subtracting from that equation?
I'm going to go through numbers so it makes sense in a second, okay? Formic acid is, I don't like that either. We'll go lactic acid. Okay, the Ka for lactic acid is going to be 1.4 e to the minus 4. So the pKa is going to be equal to 2.885. Yeah, I know the significant figures are wrong, but just live with it. All right. Say my solution. Say I have 25 milliliters of 0.1 molar lactic acid. The question is, how many milliliters of NaOH do I need to add to get a pH of 2.75? Is this making sense, guys? Okay, so you're going to do the modified Henderson-Hasselbalch, which is basically pH is equal to pKa times the log of the milliliters of your strong base divided by the milliliters of your weak acid minus the milliliters of strong base. I could go and derive this for you, but I think you'd rather just accept it. Would you rather just accept it, or do you want to see me derive it? It's 8:30 in the morning, guys. I'm not much good at deriving. Thank you. Thank you very much, Nicole. So I'm going to plug this into the modified HH. My pH that I want is 2.75. That's the one that I want. When you go to the survey, he's going to give you a target pH. Plug that in there. That's going to be equal to 2.85 plus the log of my X. That's the milliliters of my strong base divided by my milliliters of lactic acid minus X. Okay, does that make sense to you guys? Does that make sense, guys? So you're going to solve this. I'm sorry, there's one little thing I did wrong here. All right. So I'm going through and doing this. Negative 0.10 is equal to the log of X divided by 25 minus X. Next slide. 10 raised to the negative 0.10 is equal to X divided by 25 minus X. And I should know this. It should be it. What am I doing wrong here? Oh, that's what I'm doing wrong. Thank you. See, even I screw up. 10 raised to the negative 0.1 is equal to 0.0794. So I get 0.794 times 25, 19.8 minus 0.794 X is equal to X. 19.8 is equal to 1.794 X. X is equal to 11. Now, this is the milliliters of the NaOH. You need to add to 25 milliliters lactic acid to get a pH of 2.75. Okay, do you need me to go through this equation again, guys?
Can you go through it one more time?
No problem. No problem at all. Okay. The problem is you have 25 milliliters of 0.1 molar lactic acid. The question is, how many milliliters of 0.1 molar NaOH do I need to add to get a buffer with a pH of 2.75? So what I'm going to do is the pH that I'm given, that is going to be my target pH. I have to look up my Ka of lactic acid. I then plug in I plug in the log of the lactic of the constant of the log of the Ka of lactic acid. So the log of 1.4 e to the minus 4, that equals negative 2.85. The pKa is going to be negative that negative number. So the pKa is equal to 2.85. Are you with me so far, ladies and gentlemen? So my Henderson-Hasselbalch equation is going to be, this is my target pH, given that in the problem. That's going to be equal to my pKa, which I figured out from having the Ka of the lactic acid, plus the log of the milliliters of base that I'm solving for, divided by my milliliters of lactic acid minus my milliliters of base. Okay, I subtract the 2.85 from both sides. I get negative 0.10 is equal to the log of x over 25 minus x. Are we good with the math at this point? To get rid of the log, I got to raise the left side 10 to that power. So 10 to the negative 0.1 is equal to x over 25 minus x. 10 to the negative 0.10 equals 0.794. 0.794 is equal to x divided by 25 minus x. I then distributed this. Multiply both sides by 25 minus x. Next step, I multiply 0.794 times 25, I get 19.8. 0.794 times the negative x, I get minus 0.794x. Add 0.794x to both sides, I get 19.8 is equal to 1.794x. Divide both sides by 1.794, that gives me x, which is the milliliters I need to add to the 25 milliliters of lactic acid to get my pH. Is this making sense to you all? Any questions? I do not want you using the formula he gives you. For doing this last problem, I do not want you to use the formula that he gives you. I want you to use this modified version, because what he's given you isn't exactly right. All he wants you to do is put, I think, the x over the 25. Any questions, ladies and gentlemen? Do your best with the problems. I'm going to check that first one out because I think he needs to give you more information with it. I'm not entirely certain, but I think so. If he does, I will either provide the information or just more likely just say the hell with it and just let it go. So be aware of a email that's coming up. If you don't have any questions, guys, I have a dog to walk. And I got to do that before my lecture begins at 10:15. Got nothing more, guys.
Thank you.
You're welcome.
Thank you.
Take care, guys.
Thank you.
Professor, before you go, I have a question.
Is this Jennifer or Raylena?
Jennifer.
Raylena, are you still here?
Yeah, I'm about to leave.
Okay, no problem. I just want to make sure you didn't have any questions. Yes, Jennifer.
So I kind of missed the beginning of you explaining kind of the paper calculations and everything. If you could briefly go over.
No problem. I'm going to get rid of the PowerPoint right now, though, okay?
Okay.
What are you seeing on your screen?
Right now,
Nothing?
I see the PowerPoint.
You're still seeing the PowerPoint? Okay.
Now I just see us, yeah.
Okay, we good?
Now I see the canvas procedure.
Procedures. Okay. You're saying the procedures, right?
Yeah,
Okay. You have the report sheet in front of you, right?
I do.
Do I need to go through the simulation or can you figure that out pretty much
No,
on your own?
I started doing the simulation myself, but there's some things where like it asks that I'm not too sure of what value.
Okay. That's why I told you to. Remember I sent that email out that says if you get to that point, do not do the problem.
Okay.
All right.
It's the first one though. Like it says the pH.
Is this it? I'm in the virtual lab. Is this what you're talking about?
No, I'm talking about the recorded data to like briefly go.
Okay, let me get out of this then. All right, you're back on the procedures, right? You want the report sheet.
Yeah.
Okay, I'm just pulling that up. Are you seeing it?
Yes.
Okay. All you're doing the steps in the procedure
Yeah.
with one exception, and that is
That one. Okay.
this one right here. This one, you can do it if you want to. And basically all it is you're adding, I think, 3 milliliters of HCl to the buffer. Okay, that's literally, it's just an extra step. If you want to do it good, because he didn't put it in the procedures, I'm not going to be that harsh. I'm going to let it go. Okay.
Okay.
Now, what the instructions tell you to do is take 15 milliliters of your weak acid, put that into a beaker, and 15 milliliters of your conjugate base. The conjugate base, I believe you're going to be either asked to do ammonia and ammonia chloride, or you're going to be asked to do acetic acid and sodium acetate.
I think it's that one. Yeah.
All right. So you're going to take 15 milliliters of your acetic acid solution and 15 milliliters of your sodium acetate. Put them into a beaker.
Report the pH.
Did you see where the pH was in the simulation?
On the bottom. Yeah. Okay.
Okay.
So that's just the pH of both of them without no buffers or anything, correct?
Yes.
Okay.
No, that is the buffer.
Oh, the buffer. Yeah, but like no.
You are not
NaOH.
challenging the buffer at any point.
Okay.
All right. Now, to that 30 milliliter solution of buffer, you're going to add in another 30 milliliters of water. Okay.
Okay.
Then you are going to take the pH of that.
With the water included? Okay.
Yes. What are you expecting the pH to change? Are you expecting the pH to change?
I would assume.
Don't assume. Remember the Henderson-Hasselbalch, Jennifer.
Yeah.
pH is equal to pKa plus the log.
The volumes are the same. Okay. So
Are the concentrations still the same?
yeah.
If the concentrations are still the same, then the only thing that the pH is dependent upon is the pKa. And the pKa doesn't change. So again, are you expecting a pH change?
No.
All right. Now, you've got 60 milliliters of your solution. Put 30 into a new beaker. Then to the one beaker, you're going to add 0.25 milliliters of NaOH. See if that changes the pH. To the second beaker, you're going to add 0.25 milliliters of HCl. You're going to see what the pH of that is.
Okay.
Basically, what you're doing is you're challenging the buffer. And it's trying to show you that, yes, a buffer works. Okay, Jennifer?
Okay.
At this point, throw everything away. You don't need anything more.
All right.
And you're making a new buffer. The new buffer you're making is 2 milliliters of the weak acid and 20 milliliters of the conjugate base. Can you tell me off the top of your head, Jennifer, what are you predicting the pH to be?
for the
How much
20
are you going to add to the pKa to get the pH?
I mean, aren't they the same? Like
Mm-mm.
20 20?
Remember, by Henderson-Hasselbalch, they were the same as long as the concentrations were the same. Are the concentrations of weak acid and conjugate base the same anymore?
Oh, no, they're not the same.
What would you say the ratio of acid to base is?
It's a 1 to 10.
1 to 10. So you're going to put the 10 on the top, the 1 on the bottom, and you're going to take the log of 10. What's the log of 10?
Isn't it 1?
1. So literally speaking, you're going to have to add 1 pH unit to your pKa, and that is going to be approximately what your new pH is going to be.
Okay.
Does that make sense to you, Jennifer?
Yeah.
Now, to that new buffer, you're going to add, I think it says 3 milliliters of NaOH.
Yeah, it says 3.
Then you're going to add 3 milliliters of the HCl if you want to.
Okay.
It's not going to kill you. Add it and see what happens. Basically, they've got 3 milliliters of a strong acid. They're trying to see if that's going to break the buffer. That's all that's doing, Jennifer. And they're asking if the 3 milliliters of HCl changes it that much. Then you're going to throw that away. You're going to get 25 milliliters of water in a clean beaker, get the pH of that. Then to that, you're going to add 0.25 milliliters of your acid, of your HCl. See what the pH is. You're going to take another clean beaker, add 25 milliliters of water to that, and you're going to add 3 milliliters or 0.25 milliliters of your NaOH. See what the pH is of that. And basically, these are kind of like baselines. Up here, you added the same amount of NaOH to a buffer. And what it's trying to do is it's trying to show you the difference in the pHs and what happens when you add NaOH to a buffer as opposed to just adding it to plain water.
To plain water. Okay.
Does that make sense, Jennifer?
Yeah, the changes, I already plugged in the numbers and everything. So would you say that adding the HCl would make more of an acidic solution?
What do you think?
Yeah, and then if you add NaOH, it's more of a basic solution.
There you go.
Okay. All right. I think
I'm not as worried about this part as I'm worried about the second part. Did you understand what we went through?
I don't think I was there.
What I forgot to say is what you're going to do once you predict the amount of base you're going to need, you're actually going to do the titration. And that's going to be the longest part of this lab.
The second part?
In part B,
Okay.
what you're doing, you remember the calculation I went through with the 20 minus X thing, or 25 minus X?
Yeah.
You're going to do that calculation to predict how much NaOH you're going to need to add to the 25 milliliters. Actually, I think it's 20 milliliters of your weak acid solution. Then you're going to actually do the experiment.
Okay. And then you said for the questions, you might email us about more information or to see. If
Yeah, I honestly looked at this first question and I honestly, I'm looking at this first question and I don't know how he wants you to answer it. I'll be perfectly honest with you. You can't answer it like an ice diagram because you don't have
the K.
you don't have the Ka.
Yeah.
If you had the Ka, you could solve the first problem. by an ice diagram. Okay. If you had the Ka, I'm sorry, if you had the amounts of, you have the amount of HA, if you had the molarity of your A minus, you could calculate Ka through Henderson-Hasselbalch. But you don't have those two things. So I literally think that there's a problem with this problem. Unless there's something I'm not thinking of, and I'm going to email him as soon as I get off of here.
Okay.
This one, you should be fine. You've got the pKa, you've got the pH you want, and you've got that equation I gave you.
Okay, we'll just use that one. Okay.
I'm sorry, no, back off, Jennifer, let me back off there. In this equation, you are adding conjugate base to weak acid, okay? So all you're gonna have to do is get the ratio of 0.1 over 20 milliliters because the concentrations are the same. Did that make sense, Jennifer?
I just heard the concentrations are the same. That's what I heard. What
The
did you say?
concentrations are the same. If the concentrations are the same, then the only difference here is going to be the volumes. Okay?
Okay.
So what you're going to do here is you're going to plug in 4.60 for the pH, 4.12 for the pKa, plus the log. You don't know how many milliliters of B minus, but you know the HB is 20 milliliters. So it's going to be the log of X over 20.
Okay.
Does that make sense to you, Jennifer?
Yes, because we're trying to find out the volume of B. Okay.
Yes. Now, all right, yeah. All right. This one, we're adding NaOH to the HB. Okay? Concentrations are the same. Do you see that, Jennifer?
Yeah, 0.1 for one.
So if the concentrations are the same, you can use that modified Henderson-Hasselbalch I gave you. So literally speaking, you're going to plug in the 5.59 for pH, 4.54 for the pKa, plus the log of the volume of OH that you're solving for, divided by 24 minus the volume of OH.
Would you ever give us a question where it's like not the same concentration?
Not the same concentration?
Yeah.
Are we talking about like in lecture?
Yeah.
In lecture, I didn't go over this, Jennifer. And I'm not going to.
Okay.
All right.
Okay.
This is an added attraction for the lab, okay?
Okay.
And literally speaking, the face-to-face people, you would be amazed. If you'd have stuck around, if you'd have been able to stick around the face-to-face lab, Jennifer, they do so much less than you guys do.
I bet I would have liked staying, but with a
Yeah, I
certain
understand,
budget-
but my hands are tied there.
yeah, I know. So at least I'm doing good on lab though, online lab.
You're doing exceptional, Jennifer. You are really doing exceptional, and it was nothing less than I expected. And so you're going to be fine. I haven't graded Le Chatelier yet, but I did do the equilibrium one. No, the acid base, standardization of the base and the standardization of the base and the next step. And I've forgotten what it is at this point. That grade is in there. I have to do this one or the Le Chatelier, and that's going to be probably done tomorrow.
Okay, and then I did email you. I'm not sure if you saw the email. It was regarding the thinking question answers. I saw that
Yeah,
there is a
I did
module.
see that. I did see that,
Okay.
Jennifer. I just answered, I don't even know what time yesterday you emailed that to me.
I don't know. I usually get on like very late at night to do work. or,
Then
like, uh,
I haven't had the chance to answer that yet. If
okay.
I haven't answered you by 11:30 tonight, email me again, say, hey, Mr. Popovich, what's going on?
Okay.
I should have some answers for those. I just got to find them.
Okay. Sounds good.
Okay.
Thank you.
And by the way, the thinking questions are worth a lot less. I think they were worth 5 points a question last lab or last test. They're worth 2 points a question this test.
This test. Okay. I'm just trying to like review as much as possible. I'm kind of good or understanding the first 2 chapters. It's just this chapter, kind of review this one, get an idea of it.
Jennifer, if you can understand the ice diagram or the ice problems and the nuances there, then you'll do fine on this. Because literally that's about all I did.
Just the ice diagrams.
Well, not just the ice diagrams.
Well, mainly, yeah.
There's going to be at least 2 major problems with ice diagrams in them. I guarantee that. I spent that much time on it. It's guaranteed.
Okay.
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 Okay. I got a dog to walk, so I will see you later. All right.
I'll see you later as well. Thank you.
Bye.
Bye.